Okay, so there's a line on my screen. Doesn't matter. Anyway, today we are going to be deriving the Dirac equation, which I thought would be something interesting to do. I understand it's a pretty useful derivation to know, so I made some notes from a textbook, and we're gonna have a go. So, we'll start off. Well, we're gonna start off with natural units first of all. I want to define. So h bar is equal to 1, and c is equal to 1 in this new set of units. I'm not going to do any dimensional analysis. That's just what we know. And so we can look for, well, we can look into special relativity and see that the energy momentum relation for a free particle with mass m would be E squared is equal to P squared plus M squared, where P squared is the squared of the sum of the squares of the momentums of the x, y, and z values of P. So this is essentially a 3-vector, and then mass, of course, is just a scalar. Now what we'll do, or rather what we can say is, just from basic quantum mechanics, we can show some operator substitutions. So acting on our wave function, energy becomes I times the partial derivative with respect to time, and momentum P becomes minus I nabla, or del, or whatever. And so what we can do here is square the energy operator directly. So E squared psi is equal to, now we're going to introduce our operators here. So I times the time derivative times I times the time derivative times psi, that's acting on the wave function, of course, is equal to I squared times the second derivative of the wave function minus the second derivative of the wave function. Yep, that looks good. And now we can sub that into our momentum operator, which was up here. So this would actually, if we were to square that, of course I is just minus 1, so p squared, or rather, what we have up here, p squared is just minus nabla squared, or minus the Laplacian. And so we can say that the second time derivative, or minus second time derivative of phi is equal to minus the Laplacian squared plus m squared times the wave equation, the wave function, sorry. Now just bring everything onto one side, take that over is what we do, so we can say that phi times the second partial derivative with respect to time minus the Laplacian plus the mass squared is equal to 0. And this is our Klein-Gordon equation, which is correct relativistically, so it's useful, but it's second order with respect to time, which kind of messes up in single particle probability densities, because you get negative probability densities, which yeah. So what we want instead is a equation that's first order in time. And we can set that up, and we can say that the Hamiltonian operator on the wave function is equal to I times the time derivative of the wave function. People write this on the other side quite often. So what we need to do is we need to find a linear partial differential equation that satisfies our, we can say this is equation 1 and say that this is equation 2, and we'll try and we'll try and come up with an ansatz for a PD that's necessarily fulfills both of those truths. So what we want to say first of all is that the Hamiltonian operator here must be linear in its momentum components, so we can propose a general form with alpha coefficients. So h hat is equal to alpha x p of x plus p sub x even plus alpha y py plus alpha z pz, where p is the components of the momentum, plus beta m, and beta is our Massius coefficient. And what we'll actually find is that or actually, I'll leave that for a bit because it's quite cool what we find about these coefficients. Anyway, we can write a 3-vector sum notation for this. Say that this is from k equals 1 to 3 of alpha sub k p sub k plus that was the worst beta m. That's our here ak and beta are under beta are undetermined coefficients. So for this to be physically valid, squaring it must yield our energy momentum relation. So the Hamiltonian squared, what is that? It is the sum, we'll say the sum of I of alpha I pi, and then the same, but instead the sum will be over j, alpha j, not a j, is it? J p sub j, plus that sum over I again, of alpha I p of I times, I'm going to run out of space here. I wonder if this can be moved to the side. I think it can. I'm not playing Mao and I want to stop saying I wonder. Beta m plus beta, that's not a beta, beta m bracket sum over j. The reason we write it like this is due to commutative properties. Plus beta m squared. I can probably stuff that in. Plus beta m. I can write it squared. Yeah, I can. Okay. Which is the sum over I, sum over j of alpha I alpha j. We're allowed to conjoin these because these I and j are over the same domain. Pi pj pj plus the sum over I of alpha sub I beta m p sub I plus the sum over j of the same thing, slightly different order, beta alpha sub j, that's an a alpha sub j, m p sub j plus beta squared. It's not a beta squared m squared. Now we can group linear momentum terms if we let So let's j tend to I in our third term. So the linear terms both become m times the sum over I of alpha sub I beta plus beta alpha sub I p sub I. And the last thing we can do is analyze this. So if we pull that out down here, the sum over I and j of alpha j, not beta, p sub I, p sub j, is, well, rather, yeah, we can split it in, yeah, okay. So the sum of I of alpha j pi pj plus, now we know that the sum where I does not equal to j, we want it over, rather. We know that? No, we want it to be that. I alpha j. The i's and j's look like flips, and they shouldn't do that, which is why I tried to make them straight, but it didn't last very long. Pi, pj. Anyway, now, sorry, this should be I equals j. Oh, that makes more sense. That should be a j. And yeah, because then those would square. Okay, cool. So that's alpha I squared pi squared plus the sum, why they're not equal, hence I is less than j, of alpha I alpha j pi pj plus alpha j alpha I pj pi. Now, in a moment, we'll use the identity to work out why. This matters if you know about the Dirac equation, you'll already see it, hopefully. But if you don't worry, we'll be there shortly. Momentum commutes, though, because momentum's just a 3-vector, so we can factor pi pj out, because that's the same. I can put those in little brackets. So taking that final sum, this is the sum of, well, over I is less than j of alpha I alpha j plus alpha j alpha I times pi pj. Yeah, that's all good. So finally, our full expansion, I'm going to write this right on the side because I don't know how much space I'm going to have, is the sum over I equals 1. This is I equals 1 to 3 of alpha I squared pi squared, because remember momentum is a 3-vector, plus the sum over where I is less than j. In my notes I have it in curly braces. Yes, because, okay. Alpha I, comma, alpha j. I'll explain what those curly braces mean shortly. Times pi pj, plus m times the sum I equals 1 to 3 of curly braces alpha, that's not an alpha, that's an a, alpha sub I beta p sub I plus beta squared m squared. And we can say, I just used this shorthand notation. I think it's in the textbook that I used, at least. So, or the textbook, the lecture-y, notey kind of things that I found online. But again, I've seen similar definitions in textbooks. It was MIT, so it can't be that bad. A B plus BA. This is the anti-commutator. I don't know if that's the official term for it, but I think so. I haven't done or rather, I haven't specifically studied commutations in linear algebra, but it seems to make sense. Anyway, now's the fun part, because we start to compare coefficients. So if we compare our equation here to the identity, oh sorry, this should be the Hamiltonian squared. There we go. So if we compare this to our identity 1, we can call this 3. Identity, yeah, sure. We can call this 3. If we compare 3 to 1, what do we see? So there's I'm not gonna demonstrate it linearly, but we can see what everything corresponds to, in the sense that we can come out with what alpha and beta might be. So essentially, yeah, okay. Alpha sub I squared. Yeah, okay. So the first thing is alpha sub I squared is I, the identity matrix, where I equals 1, 2, or 3, which is all the things it will equal. So that's okay. Another thing, oh, I should probably write arrows or something. I don't like that. We're gonna do bullet points. Okay, bullet points. The next thing is the anti-commutative of a sub I, alpha sub I, alpha sub j, is 0, where I does not equal to j. The next thing is that the anti-commutative of alpha sub I and beta is also 0. And finally, the last thing is that beta squared is also equal to I. So we see some symmetry here, which is nice. It's good to know. Anyway, there's a fly. Doesn't matter. What the kind of the next part will be now is working out some properties of alpha and beta. So consider what we need to do is the trace analysis. So if we consider the trace of alpha sub I, we can use the cyclic property of the trace, and also the property that here the beta squared is equal to the identity matrix. Yeah, we can say I'll write down what we need to know here. So there we go. The first thing is the cyclic property of the traces. So the trace of A, B, C is equal to the trace of B, C, A. So we can say that the trace of alpha sub I is equal to the trace of alpha sub I beta squared minus the trace of alpha sub I beta times, yeah, because, yeah, okay. And now we cycle this beta to the front, so minus the trace of beta, oh goodness me, hideous beta alpha sub I beta is equal to minus the trace. I realize no, sorry. Oh, I forgot to show the anti-commutator. Sorry. Alpha I beta is equal to minus beta alpha sub I because of our anti-commutator identity. So now we can say that the trace of alpha sub I beta times beta is equal to the trace of minus beta alpha sub I beta, which is equal to minus the trace of, sorry, that should be an equal sign. Yeah, no, that checks out. Yeah, because we can take the minus outside. Alpha sub I beta. Okay, right, now I'm less kerfuffled. We can cycle this to the front, so that's minus the, I'm gonna write a tau, the trace of beta squared alpha sub I. And since beta squared is the identity, that's just minus the trace of alpha sub I. Now, since the trace of alpha sub I is equal to minus the trace of alpha sub I, this implies that trace of alpha sub I is 0. Now, yeah, okay. Now you can look at the dimensions. So, since alpha squared equals I, I can write this again. Alpha squared equals I. The eigenvalues of alpha are plus or minus 1. And the trace is just the sum of the eigenvalues. So, for the sum of plus 1, the sum of the plus 1s and the minus 1s equal to 0. So there must be an even number of positive and negative eigenvalues. So the dimension is even, because the trace is 0. Yeah. Sounds like I'm explaining to myself. Okay, so I'm telling you that because the trace is 0, the sum of the eigenvalues must be equal to 0, so there must be the sum of the plus 1s and the minus 1s must be equal to 0, so there must be an equal number of positive and negative eigenvalues. So the dimension of this matrix of alpha must be even. And the next thing is for n is equal to 2, or where n is the dimensionality of the matrix, or n is, yeah, no, n is the, yeah, n is the dimensionality. The only independent traceless matrix squaring to I is the set of the 3 Pauli matrices, but we need 4 mutually anti-commutating matrices because we have 4 coefficients. So the Pauli matrices are sigma x, sigma y, and sigma z, but we want alpha alpha 1, alpha 2, alpha 3, and beta, where these are the p coefficients and that's the m coefficient. So right, now there's a big chunk of text in my notes and I'm trying to redigest what everything means, but hopefully that provides a useful explanation. So the set of the 3 Pauli matrices is insufficient, and that's the only set for n equals 2 that would function in this case, where they square to the identity matrix. So we need another set, and hence the smallest number of dimensions must be 4, because 4 is the next even number after 2. So we know, therefore, or I can do the 3 dots, actually. Yeah, there we go. Snazzy. Therefore, n must be equal to 4 for these matrices. So they're 4-dimensional matrices. Now we will derive the covariant form because, yeah, okay. So, because it's the next step in the derivation, and then we'll do the gamma matrices, which will absorb the coefficients, and that should be everything. So this is turning into quite the mammoth video. this is our equation from earlier, kind of, minus, yeah, alpha p, where these are 3 vectors plus beta m. I'm going to drop those arrows in future, just to be clear. Again, we said earlier that p is equal to minus I nabla, so sorry, that should be equal, which is equal to minus I alpha plus beta m times the wave function. And what we want is to have a similar treating between time and space, but time has a unit coefficient, while nabla has alpha coefficients. Yeah. So we want to multiply the entire equation by beta, starting from the left. So we can say that I beta times the change of the wave function with respect to time is minus alpha beta minus I beta alpha times nabla phi plus beta squared m times the wave function, and we can pop this all onto one side. So I beta change in that with respect to time plus I beta alpha times that, I'm not going to say all the names, minus, yeah, because that's just the identity, minus is equal to 0. And the last thing that we can do is distribute the vector term, so over here. So this is going to get large, but it should eradicate all of that nonsense. So I times beta there plus beta alpha x partial with respect to x plus beta alpha sub y times partial with respect to y plus beta alpha sub z partial with respect to z, phi minus m phi is equal to 0. I promise it's equal to 0. I think it's fairly trivial how that's expanded, because a dot nabla is just these partials with respect to x, y, and z times alpha x, alpha y, alpha z, by the definition of the divergence. Now we can do the gamma matrices, so we can finally do something with all of this stinky analysis-y stuff that we did with the traces. So we know that they have to be 4-dimensional matrices. So what we'll do is define the Dirac gamma matrices. So they're super mu, or rather to the power of mu. So these are our matrices. I'm not going to put that in a box, it doesn't really mean anything. So gamma to the 0 is beta, and then to the 1 is, actually we should use identity because these are identities, is beta alpha x, squared is beta alpha y, and cubed is beta alpha z. And we can just check the property. So if we square this first one, we get anti-commutation. So that's 1 to the, gamma 1 squared would be, sorry, these are not to the power of. That's an important distinction that I didn't make. I said to the power of, but this is the second gamma matrix, and this is the third, and this is the 0th. Which I tried to make clear when I wrote gamma mu, but I don't think it really worked because my lexicon was poor. I make it very clear that this is a squaring of the first gamma matrix. So we can sub it in alpha sub x beta alpha sub x minus beta alpha sub x beta alpha sub x. And we have our anti-commutation to say that alpha sub x beta is equal to minus beta alpha sub x. This is equal to beta minus beta alpha sub x minus beta squared alpha squared sub x, which is just minus 1 times 1, which is minus 1. Hence, gammas to the 0 squared is equal to 1, and sorry, the 0th gamma and the first gamma squared is equal to minus 1. No, the ith gamma squared, because this definition actually would apply to all of them. I'm just not going to write it all out, but you could, if you don't believe me, try it yourself. Square these and then use the anti-commutation principle. Squared is equal to minus 1. So we can sub these in because the 0th gamma is just our beta. Hence the other ones must be the beta alpha x, beta alpha y, and beta alpha z must be our other coefficients, which we wrote in the equation here. So therefore I times gamma 0, the temporal derivative plus gamma 1, the x derivative plus gamma 2, the y derivative plus gamma 3, the z derivative times the wave function minus the mass is equal to 0. So this is kind of it. This is the Dirac equation. This isn't a very nice form, though. This is a pretty functional form. I mean, if you wanted to do anything useful, you could put it in this form. But this still isn't a very nice form. So what I'd like to do is put it in a slightly better form. So we can use 4-vector notation. So to say, for example, x to the mu is equal to t x y z. So this is just the position x at, I don't know, some point mu in space-time. Mu is possibly a Minkowski metric, but it's unknown. And then partial sub mu is just the partial derivative with respect to each of these things. And you can already see how this is somewhat helpful. Why have I done that? And there's a correspondence there. And so we can write our equation as, or rather we can say that what is all of this. So also we can use Einstein's summation convention, which I'll write it out again. I'll show. So gamma, the 0th gamma times partial with respect to time plus the first gamma partial with respect to x plus the second gamma partial with respect to y plus the third gamma partial with respect to z minus the sum from mu equals 0 to 3 of, yeah, that wasn't a mu, partial mu, oh sorry, that's equal to, yeah, so this is our summing notation, and further we can literally just write this as mu times partial sub mu, which is often what it gets written as. And in fact, Feynman wrote this in a nicer way, in my opinion, which is slash notation, where that is just equal to that, or rather a general form of that would be a slash is equal to gamma to the mu times a sub mu. But yeah, this is a more general form, and then subbing out the wave function here and putting this notation in is pretty funny how we can just get that for this entire craziness. But it is a much neater way of writing it, and so we get the most sort of compact form of it, which is the most beautiful in my opinion, which is that I partial slash minus m times the wave function is equal to 0. And we can put that in a very nice little, I'm going to get rid of this because I think it's ugly, because, you know, it matters how beautiful this looks very much. And yeah, I'm pretty happy with that. Wasn't as long a video as I was expecting, 36 minutes, not too shabby, lot of stuff to understand there, but you know, it's like an incredible equation. But yeah, I hope this was interesting. I hope it was some fun looking at coefficients, lots and lots of coefficients, because you know, you already really understand the fundamentals of the equation back when you're making the ansatz, because you have some idea of what it's gonna look like by then. You just have these alpha coefficients, and then you spend so long squaring the Hamiltonian and trying to find out what those might be. And it's nice that there's a useful classification of them here, with the Dirac matrices, and knowing as well that they're four-dimensional matrices is useful, because well, it shows that the equation conforms to standard space-time, unlike, you know, other theories, symmetry, and string theory and stuff like that, you know, struggle. But yeah, I hope that you found this interesting, or I hope you found it as interesting as I do. This is possibly my favorite equation. I don't know, there might be another one, but yeah, and I hope you enjoyed watching. Adios.